Hello and welcome to this video. Today we will explore the coupling between Ansys Aqwa and Ansys-Mechanical for a time domain analysis. This simple demonstration will help illustrate the general workflow. The first stage is the diffraction analysis to calculate the hydrodynamic coefficients. Next, the stability analysis, where we define the equilibrium position and introduce the mooring lines. And finally, the time domain analysis, followed by the load transfer into mechanical for the structural evaluation. Okay, so let's get started. This is the geometry of the shift hull. In Ansys Aqwa, we work with surfaces rather than solids, because these surfaces represents the areas in contact with the environmental conditions. You can see the usual way of preparing the geometry, with the origin placed at the water surface, the z-axis pointing upwards, and the water surface splitting the geometry. Now drag and drop a hydrodynamic diffraction analysis and click Edit. If you click on Geometry, you can define the water depth and density. Since the imported surfaces are opened, include Elite. Don't forget to define the point mass of the structure, because all calculations are based on it. For the mesh, use the default settings. In this case, we have around 8,000 panels, which is fine. In analysis settings, apply these two changes. Now, in wave directions, use the default values. In frequencies, you can see that the maximum is limited by the mesh size. And now we can run the model. After some minutes, you can request results. For example, the hydrostatics results table summarizes the main concept of flotation. Here you can see values for the hydrostatic stiffness, volumetric displacement, buoyancy, and stability. You can also visualize the behavior of the structure under different wave directions and frequencies. I created 5 cases, one for each frequency. At any time, you can click the play button to see the animation. Notice how the maximum and minimum pressure values change for each case. If I rotate the geometry, you can see the pressure below the water surface. Let me show you how it looks for each frequency. Finally, I requested these charts to evaluate the influence of wave direction and frequency on the response amplitude operators for each translational motion. Those are three-dimensional surfaces that you can rotate for a better visualization. Now let's move on to the stability analysis. Drag and drop a hydrodynamic response module, and by clicking on analysis settings, you will see that the stability analysis is selected. We don't need any further changes for this model, so just use the default settings. This is the wave spectrum that I will use. It's a Pearson Moscovitz at 90 degrees with a wave amplitude of 2 meters and a zero crossing period of 2 seconds. In any hydrodynamic response analysis, we can add the mooring lines. First, you need connection points on the structure defined in the geometry. I created 6 points by selecting one vertex from the surface. so this is something important to keep in mind when you create the geometry. In addition, you also need fixed points for the mooring lines. Define each point using coordinates. Visualize the points by rotating the geometry and make any adjustments as needed. Now let's create the cables. Each cable requires mass and other physical properties. These properties must be realistic, otherwise the model may diverge. Mass per unit length, cross-section and diameter, stiffness, and maximum tension are required. Each cable is modeled as a catenary. Select the pair of connection points between the structure and the seabed, and specify the cable length as needed. Duplicate the first cable and change only the connection points. Now solve the model. This will take only a few seconds in this case. Request the results, and first look at the animation based on the wave spectrum we defined earlier. Then explore the natural modes. In the table you can see which degree of freedom is most affected, and the animation helps you visualize it clearly. For the time domain analysis, drag and drop another hydrodynamic response module. Again, click on Analysis Settings to confirm that the time domain analysis is selected. Okay, here is where we define the simulation time. Make sure the initial time is set to 0, then choose the final time you want and the time step. The default value works fine in this case. Now this part is important. Select the structure, set the time range for saving the results that will be transferred to mechanical. In this demo, I will export results every 50 seconds. I will use the same spectrum but with different directions. So first propagate and then break the link to apply the changes. Finally, run the model. Now let's check some results. First, the animation. I changed the frame increment just to make the motion more visible, and you can clearly see how the structure moves. Remember that this behavior depends on the wave spectrum, the geometry, the mass, and cable properties. And what about the cables? What are the forces over time? Well, you can plot the tension for each one to identify the most critical condition. These plots are also available individually for detailed visualization. Now our final stage, but first update all modules and then save the project. Drag and drop the static structural module. Remember to update the results always. Let me show you the geometry prepared for mechanical. The geometries don't need to be identical. Here I added a few internal reinforcements to make it more realistic. And the geometry is connected to the cell D3. And we are ready to edit the structural model. Since we are working with surface bodies, we need to define the thickness and assign a material to each one. Next, create a suitable mesh and enable the inertia relief option in the analysis settings. To import the loads, click on Static Structural and open the Hydrodynamic Pressure tab. Click on Hydrodynamic Pressure and in the setup, define the result sets you want to use for the simulation. You can select a single time, a time range, or all of them. Select also all the faces of the structure to transfer the pressure. Then use the cable force icon to import all 6 forcers and remember to create one for each cable. Now run the model. The results show significant deformation, so if you're a designer, this is the moment to adjust parameters, whether by modifying the thickness, choosing a different material, or adding more internal reinforcements. In this demo, I only changed the thickness to illustrate how the results respond. You see the maximum deformation and stress values are lower, but the design needs attention. This concludes our demonstration. Thank you for watching.